Today we're going to look at the conservation of linear momentum. We left off last time talking about conservation of linear momentum, and we got this idea from Newton's second law, all right, the original way that Newton wrote it. So F net equals the first derivative of momentum with respect to time, and we talked about this last time. When the F net is equal to 0, this implies that the first derivative of momentum with respect to time is 0, which implies that the momentum has to be constant, and therefore it's conserved. Another way to think about this, which can be handy, is to write the derivative as delta p over delta t. And if that equals to 0, then you can also see that delta p equals to 0, which means that p final minus p initial equals 0, which implies that they have to be the same thing. And so whenever the net force is 0, momentum does not change, and we say the momentum is conserved. And one thing just to be real careful of, technically this is linear momentum. However, most people consider this just momentum. There are other kinds of momentum that we'll talk about later, and so I'll probably slip up a lot and say linear momentum sometimes and just momentum other times, but it's really just the same thing. So this makes sense that when no forces act on a particle, there's no change in momentum, right? This is just Newton's second law. All right, if there's no force, there's no acceleration, no change in velocity, and since for a particle the mass can't change, we're assuming the mass can't change for a particle, then the momentum can't change either. So nothing really new here. It's actually pretty boring. However, if we consider a whole system, this turns into a very useful idea, and a system is just a group of objects that interact with each other. We're talking about a system. We can break our forces into two kinds of forces. There's internal forces, forces that objects within the system exert on each other, and then there's external forces, forces exerted on the objects by something that's external to the system. Now if we think about this, let's look at a system like of ball A and ball B, and let's say for instance that ball A and ball B collide. All right, at the moment they collide, they're going to apply equal and opposite forces on each other according to Newton's third law. There'll be the force of A acting on B and the force of B acting on A. And so let's look at Newton's second law over here on the right. If we split up the net force, the total force acting on either of our objects, okay, or actually let's think about the net force acting on our whole system, all right, then we can break it into two kinds of forces, those that are external and those that are internal. What always happens is the internal forces always come in pairs, and due to Newton's second law, Newton's third law, they're always going to be equal and opposite. So the internal part for a system is always going to cancel out. And so that's going to equal to 0, and so we can rewrite Newton's second law for a system like this right here, that the net force of all the external forces acting on it equals dp dt. And so this changes things a little bit for a system. And so Newton's second law for a system looks like this, and what this implies is that the total momentum of an isolated system remains constant. By isolated, okay, isolated means that the external force net sums up to 0. And so when this is equal to 0, then that means dp dt is equal to 0, and the momentum can't change. It can be transferred between objects, okay, but the total momentum of your system can't change. And this is a really powerful idea. A really nice example is looking at billiard balls. Okay, if you have two billiard balls collide, all right, if we neglect the friction of the table, which is a pretty good approximation, all right, what happens is the balls are just going to transfer momentum between each other, all right, but the total system of all the balls is going to have the same amount of momentum. It's just going to be transferred between the balls. So this is a very useful idea, and you're going to see that the math isn't so bad in some cases, but I think what's harder for this is to figure out when you can use it. And so just one little key, conservation of linear momentum is very useful for collisions and explosions. In fact, whenever you have either one of those, it's probably the first thing you're going to want to look at. Okay, collisions and explosions, the forces are generally very complicated, very non-constant, and so it's not very good to approach it F equals ma style. Conservation of linear momentum gives us a very useful way to solve these problems by treating them as a system. And also a little hint here. So technically, okay, conservation momentum only works when there's no external forces. And there'll be a number of problems where we'll say there's no external forces. But actually, in reality, even if there are external forces, these forces are generally very small compared to collision forces. For instance, an automobile's crashing, an automobile accident, okay, the friction that you would have with your tires as you're skidding into this collision is so small that actually the cars, to a very good approximation, conserve momentum. And so almost always you can conserve momentum in any kind of a collision. Okay, that's really important because we're going to have lots of collisions going on from here. Now, to actually solve these problems, we want to somehow use the fact that the momentum is equal. And so there's lots of ways to do this. The way I like to do it is just right here to say that momentum initial equals momentum final. And then what does that mean? Well, that's going to be the sum of the momentum equation for all your pieces initially equals the sum of all of them finally. Now, this is a vector equation, and so now it'll be rare for us to have more than two directions, but you could have three in principle, but for this class we'll only have two. And so basically there's two equations, one in the x direction, one in the y direction. And again, the tricky part is going to be when you can use them. And just a little short rule of here, generally a lot of our, probably at least half of our momentum problems, if not more, will depend on only two objects. And so when that happens, when there's two objects, you just basically write out mv initial for the two objects and mv final and set those equal. And of course, if there's three, you just add another term on each side. All right, so let's look at some examples. So here's a bomb of mass 45 kilograms and it explodes into two pieces. The first piece of mass 15 moves off to the right with a velocity of 10 meters per second. So the first piece moves off 10 meters per second. It's got a mass of 15. The second piece moves off with what velocity? We want to figure that out. So pause it, work through this, and see what you come up with. We'll talk about it in a second. All right, when I did this, I came up with 5 meters per second. So let's look at this. So first of all, is momentum conserved in this problem? And if so, in what direction? Well, I've drawn a picture after the explosion happened. And if you look here, okay, the forces acting on the two objects would be mg going down. Now, there were forces acting beforehand, but they were all internal forces of the bomb acting on itself. Okay, and so if we draw our usual y-x diagram, momentum is conserved in the x direction. It is not in the y direction because there's gravity, but we don't care. The x direction is all we're going to need to do this. So by setting this up, I'll take my little handy-dandy equation. Now initially, the momentum was 0. You can see right here the momentum was 0 initially for all this. And so afterwards, it's going to be 15 times 10. That's for this guy here. And we'll call the 10. I'll make that positive. And so we'll just call going this way to be the positive x direction. Then afterwards, you've got 30 times v final. Now, we have a pretty good idea that this v final is going to be in the negative direction. But my rule is just to keep it as a positive number and then see what's going to happen. Okay, you can usually get the equations will tell you whether it's negative or positive. And so if we look at this, I can rearrange everything to get looking like this here, that 15 times 10 equals negative 30 times the velocity final. All right. Now, it's important to note here that when initial momentum of a system is 0, so initially when it's 0, the final momentums must add up to 0. And since there's 2, they have to be equal. So the absolute value of these two sides have to be equal to each other. And if you go through and solve for this one, I get negative 5 meters per second. Now, that's one dimension. We can also have these problems in 2 dimension, and that's where the math can get a little bit trickier. All right, but all that is, we have the same equation, just we have it twice, once in the x and once in the y. And so here we're going to go through and just do kind of a typical 2-dimensional example, and so we're dealing with hockey pucks. And so here we have a situation, so you can read through this problem here. So a gray hockey puck initially has a velocity of 10 meters per second. It collides with a green hockey puck, which is initially at rest. The green puck is seen to go off at an angle of 35. The gray puck comes off at an angle of 55 below the x-axis and has a velocity of 5.73. We want to know what's the velocity of the green puck. So here would be our picture. So the gray one, so initially the gray one's moving, the green one's not, and it comes in and they move off at these angles, sort of like in this picture here. And so our question, as always, is momentum conserved and in what direction? These are hockey pucks. They're on ice, and so you can assume that in the XY direction, typically, let's write it this way, X and Y, there are no external forces. The only forces are forces between the pucks. And so no outside forces in any direction, so momentum is conserved in the X and the Y directions. So good, we can use X and Y equations. And so here's our initial picture, v equals 10 meters per second, so again I'm going to call that in the X direction, and then the other guy, the green one, is not moving. The final picture is a little more complicated. Okay, the green one goes off at 35 degrees and the gray one goes off at 55. So we're going to have to use some trig in that case right there. And here is, we don't know what the velocity of the VB of the green puck is. We do know the velocity of the gray one is 5.73. And so here I can use my trig and say, okay, I don't know what this velocity is, but since I know the angle, I can make a little triangle here. And so the X direction will be VB cosine 35 right over here, and then the Y direction will be this guy over here, VB sine 35. And a similar thing for the gray puck. I can make a similar sort of triangle for the gray puck, like this and like this. And then again with using the angles. And so for the gray puck, I can see that its X value is 3.28 and its Y value is negative 4.69. This is where I think this stuff gets pretty tricky mathematically. So make sure that it makes sense where we're getting all these angles from here. Once you have those, you can write your equation. So let's start with the Y direction momentum. Now in the Y direction, neither of the pucks are moving initially, right? So the Y direction is sort of like, we have X going this way and Y going this way. The pucks are moving this way initially, not up and down, so it's 0. And then afterwards, we've got negative M 4.69. That puck is moving downwards in the Y direction. And then MVB sine 35 for the other guy. We're told that the two pucks are identical, and so the mass will be the same. And so we can rearrange our equation like this, and what's really nice is I can cancel out the mass. This will happen sometimes in your problems, and it's really fun to do that. And then here I can solve for VB. Automatically it's 8.2 meters per second. Because I wrote it in here with this sine of 35, I can solve for that velocity, no problem. Now this one wasn't too bad. We only needed the Y direction info. But what's nice is with these kind of problems, you can always have another equation. So let's just go by and make sure that the X direction works. So in the X direction, initially that gray puck was going with a velocity of 10 meters per second. Afterwards, the the gray one's going off at 3.28, and we just solved for the answer for this guy over to here. So first thing is I'll cancel out my masses. Again, that feels really good to do that, so I'll just do it. And then here I've got 10 equals the 3.28, and then 8.2 times cosine 45, and you'll see that when you add this up, it pretty much, within my calculational error, is correct.